let's look at this exercise 1.1.4. Firstly, show that if you have a R module chain complex C, and then you apply the covariant functor Hom and R module from A, then again you have a chain complex. A chain complex of abelian groups. So firstly, this is abelian group, which means this is a Z module. Each Hom RACN is a Z module. Actually, it's because this R module form abelian categories, in particular the Hom set is a Z module. Or you see it directly, check it directly. And it's easy to check this again for complex abelian groups. You just have to describe what is this new complex after applying Hom. It's just a map you realize. Which maps homomorphism F to a new homomorphism, which is composition of dn with this F. Because this is covariant functor, if you have a map F from A to Cn, compose with dn give you a map from A to Cn minus 1. So let's define this map, and obviously this is a cochain. This is a chain complex, which means composite twice gives you zero. Okay, and then what is left to check for the exercise is if the homology module is 0 for this new complex, then show that the original complex is 0. Let me see. This is what we want to show. Show then quotient Bn is 0 if knowing that this is 0, which is 0, this is 0. Knowing that this is 0, and we want to show that then quotient Bn is 0. And then let's just apply the definition. What does it mean? Hn of the new complex is 0. It means the kernel dnh quotient by image dn plus 1 h is 0. I denote by h to distinguish between dn of the original complex and dn of the new complex. Okay, so by definition, these are the morphisms from Zn to Cn such that dn compose f equals 0, and the image dn plus 1 are those morphisms of the form dn plus 1 composed with J, where J is morphism from Zn to Cn plus 1. Suppose you already know this is 0, which means what is quotient J? Which means every morphism f killed by dn could be written as the form of the image of dn plus 1 composed with some G. And in particular, this implies that dn quotient Bn is 0 because what does it mean to say any kernel is in the image? It means that if you have an element in Cn that is mapped to 0 under dn, you want to show that there exists an element in Cn minus 1 that is mapped to this element in the kernel under dn plus 1. How can we show that? Actually, I just have to take a particular f in kernel dnh. I'm going to take this f to be the identity. And so what is in the kernel DNH? A particular element in the kernel DNH is the one which embed Cn in the kernel Dn into Cn. And it's killed by Dn. Sorry, I should say it like that. So notice that there is a particular element in the kernel DNH. Recall that the elements in the kernel DNH are those killed by Dn. In particular, the inclusion map I is contained in the kernel DNH because I is killed by Dn because our A is taken to be by the question A is taken to be the kernel of Cn, and so the inclusion map from Zn to Cn will be killed by Dn because by definition Zn the kernel of either Dn. And so for this particular f, there exists some g from Zn to Cn plus 1 such that Dn plus 1 compose g equals f. What is f? F here, as I said, f here we're taking to be the identity, which means that for whatever element x in Zn, you apply to the equality Dn plus 1g equals f on both sides. F is the identity map. It tells you for any element x in Zn, Dn plus 1 gx equals x. This is telling that gx is in particular element and is mapped to x through Dn plus 1, which means x is in the image of Dn plus 1, and one pre-image is gx. Okay, so the second question, the left question, is the converse true? Honestly, I'm kind of confusing why this question is asked, and not confused about why it is asked, but confused about what phenomenon does it want to say. We would guess it's not true, and so give a counterexample. The way we should do that is try to think about if you need a chain complex with each and 0. So in particular, you could give the example of a cyclic chain complex, which means exact sequence. And then the question would be asked if Hom functor, not arbitrary Hom functor, but the Hom functor with Zn in the position of A, which means this functor, but not arbitrary A, but we want Zn. An exact functor, for example, because if it's not exact, then you could find some degree n such that corresponding chain is not 0. And we know this is not exact, but you know that when Zn is projective, this will be exact. So you have to give example to avoid Zn being projective. You have to find example of Zn not being projective. For example, we know that Z quotient by some integer is not free Z module. I was trying to use that example to construct the example. At the beginning it doesn't work very well, then I modified it. I think this is an example. So I construct the exact sequence of Z modules, call it C dot, right? Call it C dot. Show this one, inclusion 2Z into Z, and then quotient by 2, surjective map into Z quotient by 2. Then you see this is short exact sequence, and so in particular the Hn or 0, in particular H0 is 0. And now you apply this functor Hom Z quotient 2 at Z module. In particular, we know this is not exact. It will no surprising. It will not have the surjectivity. Not always, but there should exist some example such that this will. There should exist some short exact sequence such that we apply this functor is no longer surjective. For example, let's test this one I constructed. So you apply this C quotient 2, and then the first two terms, they're all consisting of only 0 element because they're not of the same characteristic. You can only map everything to 0, otherwise you could not define reasonable image of one bar, right? One bar could only be mapped to 0. And notice this term has two morphisms, the identity one and the 0. And so the kernel quotient image tells you that it's not a 0 group. So if I encounter example,